Hello, this is Professor Keen. Today I'll be talking about pendular motion and its relationship to harmony. The reference is from a student's guide through the grade physics texts, volume 2, chapter 5, and this is from day 1 of Galileo's Dialogues Concerning Two New Sciences. You might recall in the last lecture, which was from chapter 4, Salviati, Segredo, and Simplicio raised an interesting question in the context of talking about pendular motion. And this question had to do with music. In particular, they are wondering why it is that certain combinations of notes sound good when played together. So, for example, if I pick out two notes separated by an octave on a piano and strike both of those notes together, they will sound pleasing to the ear. But if you were to take some random two notes on the piano or some combination of keys and strike them together, it will generally sound quite horrible. And so the question is, why is it that certain combinations sound good together, whereas others do not? And I should emphasize that this is not something this seems to be something that goes across cultures and across different time periods. It seems to be kind of a universal recognition. So while certainly we have different tastes in music and so on, we're asking a more specific question here about certain combinations of notes and why they are pleasing to the ear and other combinations of notes are not. So in order to answer this question, which really delves into music theory, what we're going to do is look a little bit more carefully at pendular motion and its relationship to mathematics, and then come back around to this musical question. So the first thing that Salviati mentions at the beginning of this chapter, this is right around page 60, is he notices that he says, first of all, one must observe that each pendulum has its own time of vibration so definite and determinate that it is not possible to make it move with any other period than that which nature has given it. So in other words, we would say that every pendulum has a natural frequency. That's the more modern term for it. Every pendulum has a natural frequency. If we wanted to attach a letter to it, we'd call that F. Sometimes it's F naught, F with a little zero down below it. A natural frequency, F naught, at which it will swing. If pulled back and released. Right? So remember, the relationship between frequency and period is that the period is equal to 1 over the frequency. So saying that it has a natural frequency, maybe 3 times per second or 5 times per second, implies that it has a natural period of time that it takes to swing back and forth once. And this is called the natural frequency. And what Galileo does is he goes on to mention that if you were to pull back a pendulum and to release it and look at the natural frequency at which this vibrates, different pendula are going to have different natural frequencies, right? So if you have a pendulum that is quite long, then it's going to have a longer period oscillation, a smaller or shorter frequency, and a very short pendulum will have a very small period or a high frequency. And here's the other point that he makes. He says that if you want to get a pendulum swinging, the best way to do that is to drive it at its natural frequency. So if driven or pushed at its natural frequency, I'll be more specific in a moment, but at its natural frequency, then then its amplitude will increase. So you're probably familiar with this. So when you have your little brother or your little sister on a swing and you want to push them, well, what you could do is if you want to be scientific about this, you could pull them back on the swing, release them, and use a stopwatch to measure the time it takes for each swing, and you could calculate the frequency of the swing then. Okay, so that would be determining the natural frequency. But let's suppose you wanted, instead of pulling them back and releasing them, you wanted to push them to get them swinging, or you wanted to keep them swinging. How should you push them? Well, there's kind of natural ways to do this, or intuitive ways to do this, and then bad ways to do this. So if you push them once every time they swing, so when they come all the way back, then you push them forward, and then you wait for them to come all the way back, and you push them again. So your pushes or your shoves are at the same frequency as the natural frequency. Then what happens is the amplitude of the swing will get bigger and bigger and bigger. But if, on the other hand, you try to push them too often or not often enough, at sometimes you'll be fighting their swing, and other times you'll be helping them, but sometimes you'll be fighting them, and it won't work as well. Their amplitude will not increase. You might even decrease their amplitude. So this is the idea that there's sort of a driving frequency at which these pendula can be pushed that will maximize their gain in amplitude. This doesn't apply merely to pendula, it also applies to musical instruments. Okay, so let me make a couple of other comments here. So this is the next point that Galileo makes, which is related to this previous point I just made. So musical instruments can exhibit, and again, this is not the term that Galileo uses, but we will use it. They can exhibit sympathetic resonance. What do we mean by sympathetic resonance? That means that when a nearby instrument is struck, that has the same natural frequency as the distant instrument, the one that's separated from it, as the distant instrument, they will both vibrate. So for example, if you have a guitar and another guitar that's more distant, and you strike one of the notes on one guitar, the note on the other guitar will begin to vibrate ever so subtly at the same time. Why is this? Well, the explanation that Galileo provides is that when you pluck one guitar string, what will happen is the air that is adjacent to that guitar string will be pushed forward. And then when the guitar string vibrates back and forward again, it will push it again. And so the air is being vibrated at the same frequency as the guitar string. And these vibrations of the air will travel across space to the other guitar, and they will strike those guitar strings with the same frequency as had been produced by the original guitar string. Now, some of the guitar strings on the second guitar will have a different natural frequency than the frequency you're driving it at. But if one of them has the same natural frequency as the puffs of air, then that one will begin to vibrate as well, because you're pushing it at just the right frequency. So those two instruments will be said to be exhibiting sympathetic resonance. Okay? Another thing that Galileo brings up is that when a rim of a goblet is rubbed, when the rim of a goblet is rubbed, it emits a note, a musical note. So it emits a note, and standing waves of water appear on the surface. We'll be more precise about what we mean by standing waves in a future lecture, but I think you know what I mean. There's going to be little waves of water appearing on the surface of the fluid filling the glass. They're little ripples, usually concentric circles. In the glass. Okay, so you might imagine if you have a goblet like this, right? And you put some wine in it, right? So here's your wine in your goblet. And if you were to rub the rim in a circle, you wet your finger and rub this, you will notice these tiny ripples that form in the surface of the wine. And you could look at the separation between these ripples. And the separation between them is going to be related to the pitch of the note that's being emitted. And this is something that Galileo notes, that sometimes as you're rubbing this and you look at the distance between these ripples, so there's going to be some note, some frequency, or some pitch. The pitch is, oops, let me go back here, misspelled that. The pitch is related to the ripple separation. Right, so if you think about the distance between two peaks of these ripples, that's a ripple separation. The pitch is related. And here's the thing that Galileo notes. He says occasionally as you're rubbing this, suddenly the pitch will jump up by an octave. So occasionally the pitch, it will suddenly become higher pitch. The pitch will jump by an octave. And when that happens, the distance between the ripples is halved. So the distance between the ripples is halved. So when the pitch goes up by an octave, the distance is halved. And this suggests a mathematical relationship between these pitches. So an octave, Salviati concludes, so an octave is associated with either a 1:2 or a 2:1 ratio. An octave is somehow associated with a 2:1 ratio. Okay? Now, before we go on and talk more about octaves and their relationship to mathematics, let's review a bit of music theory for those of us who are not musicians. Those of you who are probably know this already, but let's do a quick review of music theory, just some very simple aspects of it, because these terms are going to come up throughout this text. So the term octave is associated with a 2:1 ratio. And we'll be more precise about what is this 2:1 ratio, what does this mean? But let me just write these down first. Then the term a fifth will come up. By the way, Galileo is himself very interested in music theory. His father was a musician, and he spends a considerable amount of time thinking about the relationship between music and science and mathematics. So the fifth is associated with a 3:2 ratio. A fourth is associated with a 4:3 ratio. A major third, I am not a musician, so if I get any of these wrong, please forgive me. Major third is associated with a 5:4 ratio. I looked these up recently. A minor third is associated with a 6:5 ratio. I wish I knew more about music. And a major sixth is associated with a 5:3 ratio. Okay, so those are just some terms that are going to be coming up. These, by the way, can be studied using a very simple musical instrument called a monocord. And Galileo talks about this. He says you can study these ratios with a monocord. And let me draw a monocord so you know what I'm talking about here. So a monocord, think about the most boring instrument you could possibly imagine with a single string on it. Okay, so you take a board like this, and on the end of it maybe take a pulley, and then on the board you have a couple of little triangular wedges. I don't know if you make these of wood or something. And then what you do is you nail down a wire. Make the wire a different color so it's a little more obvious what's going on. Let's make it a, I don't know, make it a green wire. You nail down this wire right here. It stretches over these two and then over the pulley, and then you hang a weight right here to maintain some tension. Okay? And the length of this string, I guess the distance from here to here, let's denote that by L, the length of the string. And also, so the weight is W, and the string is going to have some mass per unit length. We'll call that Greek letter mu is mass per length. You know, a very thick string will have a high mass per length. The thin string will have a small mass per length. L is the length between these two. So if you pluck this, the note that it makes is going to depend on the length. It's going to depend on the tension, that is the weight you're hanging here, and it also is going to depend on the mass per unit length. So this is what we mean by a monocord. And one of the points that's being made here is if you keep the weight constant, so you keep the tension constant, and you don't change the string, you have the same mu, you can strike notes having different ratios of pitches depending on the length. So you could take some kind of a bridge and place it right here to make the string half as long. You could pluck this and you'll get a note, and then you take the bridge off, pluck it again, you get a different note. And when the string, it changes by a length of 2, so you go from a length of 1/2 to a full length, the notes will be separated by an octave. That's where this 2-to-1 ratio comes in. So the longer string is going to be a lower note, a string that's half as long will be a higher note, and those are separated by an octave. You could, if the ratio of the lengths is 3-to-2, and you strike these, you have to think about where to put the bridge to do that. So maybe you put it a third of the way down, so you have a length of 2, and then take it off, and it's got a length of 3. Then those two notes will be separated by a fifth. Likewise, you could have two notes separated by a fourth, a major third, and so on by adjusting the length of this monocord. This is one of the ways that these relationships between notes can be ascertained. Okay? Now, let me ask a question, and then we'll come back to this in our next lecture, because I don't have space or time to talk about this right now. But if you change the length by a 2-to-1 ratio, you get two notes separated by an octave. But there are other ways than changing the length that will change the pitch of notes, or the sound of the note. And by keeping the length the same, but by changing the weight, that is the tension in the string, or changing the mass per unit length, you also can get two notes separated by an octave. But it just so happens that you need to quadruple the tension. So if you'd have kept the length the same and the mass per unit length the same, you would have to quadruple the tension in order to get a note that goes up by an octave. So why is it that we associate 2-to-1 ratio with the octave? Why don't we associate the octave with a 4-to-1 ratio? Because after all, if you need to quadruple the weight, quadruple the tension to get two notes separated by an octave, why shouldn't we say the octave is a 4-to-1 ratio? This is the question that we're going to address in my next lecture.